Hello, everyone. I am Dr. Reza Said Kandezi, and in today's discussion, we'll focus on IEEE 1100, which is commonly referred to as the Emerald Book. This is a recommended practice that outlines the principles and the techniques necessary for powering and grounding sensitive electronic equipment in the environment where the reliability and the signal integrity and electromagnetic compatibility are important. Now, we are going to cover the system framework, which means that the design, implementation, diagnostic, and some of the future proofing aspects. And we are using the IEEE 1100 as the framework for this discussion. Now, uh, as we said, the IEEE 100 is a recommended practice, is not mandatory standard, and it provides engineering guidelines for the powering and grounding of the sensitive electronic equipment, which we call it SPE. This standard aims to prevent the failures or data corruption or operational disruptions in the environment where even a minor electrical disturbance can cause significant damage or downtime. Now, let's talk about why this standard exists. The traditional grounding methods are normally safety focused. Okay, so it's designed to prevent electric shock or fire. So, however, there are some sensitive electronics like computers or medical equipment or telecom systems that they need a functional grounding approach. Okay, so that aspect actually prioritize the signal integrity or low noise reference planes and transient suppression instead of just safety focus. Now, there are some key objectives in IEEE 1100. One would be the reliability enhancement, which the goal is to keep sensitive electronic systems running continuously without any unexpected shutdowns or data loss or malfunction. But how we do that is through the designing the power distribution and the grounding system, so we could avoid the tripping or tripping of the breakers. Another kind of like approach for this goal is to preventing the logic faults. Okay, when we talk about the microprocessor, which could misread some data due to the ground noise. Now we are going to minimize also the memory corruption when we talk about the digital system that is caused normally by voltage transient or a ground bounce. We also would have protecting equipment for physical damages that could happen because of the power surge or the harmonics. Now, there are another aspect or objective, if you want to be more specific, for this standard, which is functional grounding for the electronic devices. So as we said, the traditional grounding is mostly focused on safety. So it's basically focused on to clear faults and protect the people. But the functional grounding that we want to talk about is basically creates a stable low impedance reference plane for the signal circuit basically. Now, as we said, one of the key functions of this type of functional grounding is the signal integrity, which is basically reducing the common voltage differences between systems to basically prevent logic errors. Now we are going to have noise immunity function, which is suppressing high frequency transient, which can couple into the data lines. Now, we also have the voltage reference stability as a function of these functional grounding, which is bounding and grounding, and they are designed to maintain consistent reference plane for all the interconnected devices. Now, another goal for this standard is to surge and transient protection. Now, why this is important is because the transient from like lightning or switching surges or inductive load switching, they can damage sensitive electronics and cause some errors in their function, in the operation of those devices. Now, what the IEEE 100 recommends is to use surge protected devices so we could properly coordinate with the grounding system and protect the system from the surges that are applied due to various reasons. Now, proper bonding is also recommended to give transient a low impedance pass toward the ground rather than through the sensitive electronic systems. Now, this standard also recommends coordination with the family standards of IEEE 62, which is the surge protection standard. Now, we have another purpose as power quality conditioning, which provides, which is actually the goal is to provide clean, stable, and regulated power for those sensitive equipment that we are covering in this standard. These problems could be, those power quality problems could be voltage sags or swells, which can cause computer reset or UPS transfers. We could have problems like harmonics that generated by nonlinear loads and can overheat transformers or actually distort the waveforms. We could have flicker and high-speed transient, which cause malfunctioning of the control electronics. And the solution is for dealing with those problems is to use isolation transformers or redundant feeders or UPS system, as well as harmony filters, which is recommended for enhancing the power quality conditions in our system. Now, IEEE 1100 is very important and plays a critical role because that IEEE 1100 is performance oriented. So it's designed for mission critical environments, okay, like data centers or healthcare facilities or broadcast and telecom systems or even like industrial automation. Now, who should use this standard, the IEEE 1100? We have several kind of like different type of engineering and facilities that use this standard. One would be the consulting engineers. Okay, so these consulting engineers are basically responsible for designing the electrical infrastructure in a mission critical facilities like data centers or hospitals or telecom hubs. So this IEEE 1100 provides for those consulting engineers with an engineering best practices that goes beyond the safety to ensure power quality or noise suppression and the system uptime. Now, the key applications are like, for example, data centers. Engineers must design hybrid grounding systems to make sure a low common mode voltage, normally less than 1 volt RMS. Also, another kind of like environment that could use these, the consulting engineer can use these a standard is hospitals and the laboratories. So it must specify isolation transformers and redundant UPS systems so they could meet the medical equipment sensitivity requirement. Now we could also use that in an industrial system when consulting engineers use the standard actually to separate like the zones of our system. We are going to talk about that. We have zone A, which is the sensitive electronic, or zone C, which is the motor drives. And this should be with a proper load segregation and filtering. Now, a design failure can lead to the data loss, production downtime, or even life-threatening failures when we talk about the medical systems. So basically, this IEEE 1100 is very important and essential for the consulting engineers, so they could design the verification checklist for those sensitive electronic equipment based on the criteria defined in the standard. Now, facility managers also can use this standard. Basically, they are responsible for ongoing operation of the power and grounding infrastructure. So this IEEE 1100 helps them to detect and mitigate the issues proactively, okay, before they cause system failure. Now, there is some responsibility that is for the facility managers that is mentioned or like covered in IEEE 1100. One is the monitoring grounding impedance and common mode voltage, which they have to make sure that their target grounding impedance is always less than 1 ohm and maintain a uniform signal reference. And they have to keep the common mode voltage under the 1 volt RMS so they could prevent logic malfunction. Now, there is a periodic inspection of the signal reference grid, bounding network interference, and the surge protective devices defined for the facility managers in IEEE 1100, and they are defined to make sure that they remain within the operational specifications. Now, another aspect that this standard could help the facility managers is load management. So they could make sure that the sensitive loads remain isolated from the noisy equipment. So IEEE 1100 would do that by the zone segregation that we are going to talk about in our upcoming slides. Now, if we have a poor grounding or we ignore the power quality issues, okay, so this could end up the facility manager's responsibility. It's basically their responsibility, and they have to make sure that they prevent those problems. Now, in other groups that could benefit from the IEEE 1100 is the electrical contractor. Now, normally electrical contractors are tasked with the implementation of the design, power, and grounding system. So even if the engineer's specifications in the design was accurate and proper, the improper installation can compromise basically everything. Now they have to make sure that they have proper grounding and bonding. So basically found isolated ground bars directly to the SRGs for sensitive loads, or maintain neutral to ground bound only at the source transformer, so they could avoid circulating the ground current. Another aspect that is mentioned for the electrical contractor is that they have to use twisted pair or shielded conductor for the long distances and long runs, and run the hot and neutral and the ground conductor together in the same conduit. So they reduce the inductive noise coupling. Now, improper practice done by contractor, like bounding ground at a multiple points or sharing neutral conductor basically can nullify the entire functional grounding strategy and lead to the logic faults or equipment damage. Now, there are some essential environments that IEEE 1100 would support and cover. These sensitive equipment exist basically everywhere, but some environments are uniquely vulnerable. Now, one would be the data processing center. So IEEE 1100 is essential because continuous uptime is critical for business operation, cloud service, and data integrity. So even a millisecond power disturbance can corrupt the database or crash the servers. So also the data centers operate with a high density and sensitive electronic equipment like servers or storage arrays and networking gears, which are highly susceptible to the voltage sags or transient and the ground noises. Now, IEEE has some key practices like hybrid grounding and signal reference grid, which we know as the SRG, signal reference grid, which basically is a multi-point grounding or SRG for high-speed digital racks. So make sure we have a common mode voltage under 1 volt RMS. Now, there is another practice which bounding all the racks, cable trays, and shields to the SRG so they could maintain the equipotential planes. The IEEE also recommend redundant power topologies, which is a secondary selective system with the dual UPSs and backup generators, so they could maintain like a tier 3 plus reliability. Isolating transformers also is recommended to suppress common mode noise from upstream feeders. And there are also some practices for harmonic control, which is using the K-rated transformers and harmonic filters for servers with high nonlinear loads. Now, there are some another essential kind of sensitive environment, which is the healthcare facility. We know that medical equipment like MRI or CT scanner or surgical robots and patient monitors are life critical. So even momentary power anomalies can cause diagnostic error or surgical interruption and very harsh consequences. Now, IEEE practices are some of the IEEE practices that are recommended for this kind of environment is the functional grounding for medical electronics or a strict voltage and transient control. Or one of the other recommendation is to have a clean power supply, which normally there is a double conversion UPS system with plus minus 2% voltage regulation and plus minus 0.1 hertz frequency regulation for like radiology suites. Now, there are also broadcast stations that are sensitive and considered as essential environments for IEEE 1100. But TV and radio station, which in them, the signal quality and continuous transmission are basically mission critical. Now, IEEE suggests several practices for those environments like grounding strategy or EMC, electromagnetic compatibility and surge protection, or node isolation. We have industrial automation on in the essential environments. It covers like a SCADA or PLC networks and robotic installation control, and that control entire production lines. and any disturbance can lead basically to the production downtime or safety hazard. For those environments, IEEE recommends some practices like load segregation and zone design. Another practice is grounding and signal integrity. And another practice also is the surge and harmonic control. Now, if we don't use those practices, it would be like, for example, industrial automation, it would be unexpected production shutdowns or robotic malfunction or even hazardous conditions due to the logic errors in PLC or communication pods. Now, IEEE is not exist in isolation. It complements and extends. Now, this standard is not a standalone standard. It is recommended practice specifically for sensitive electronic equipment. Now, proper integration makes sure that we have regulatory compliances, power quality and noise mitigation, and grounding integrity and system reliability. Now, we have some key standards that are integrated with IEEE 1100. One would be IEEE 519, which is harmonic control for power system. This standard specifies maximum harmonic voltage and current distortion and the limits to prevent overheating or transformer derating and waveform distortion. Now, we have IEEE 142, which is known as Green Book, covers the grounding of industrial and commercial power systems, and the purpose is for that standard is to provide fundamental grounding topologies for industrial and commercial systems. Now, another complementary standard is IEEE 62, which is a family standard, and it covers the surge protection, which basically this standard provides guidelines for surge protective devices and their design, selection, and coordination. We also have the standard NFPA 70, or we could call it National Electrical Code, NEC, which basically sets the minimum electrical safety standards for wiring and grounding in the electrical system. It makes sure that the fault curing and personal safety is meeting that NECs make sure and defines the criteria for those aspects. And basically, IEEE 100 extends these to ensure also we have a functional reliability. Now, there are some key definitions that we need to mention, and it came from IEEE 1100. One would be the sensitive electronic equipment that SEE refers to any electronic devices or system that failure or misoperation or data corruption due to electrical disturbances can cause data loss or production downtime or safety risk and financial losses. Now, the key characteristics of that definition is that on those equipment is that the high susceptibility to the power quality issues like voltage sags and transient and harmonics and EMI are very effective and influential for those devices. For example, when we have data servers or PLCs or SCADA systems, or medical imaging equipment, or even broadcast transmitter, and avionic system, they are very sensitive to those disturbances and the loss of the power quality. Now, IEEE 1100 recommends clean power, which means voltage regulation within ±5% and the THD less than 5%. It also recommends low noise grounding and zone segregation to make sure we are meeting the proper criteria for those sensitive devices. Now, another definition that we have to mention is the signal reference grid. We call it SRG. Now, the SRG is a mesh of interconnected conductors, normally copper strips, that forms an equipotential reference plane. Okay, now material of these SRGs are normally copper. There is a typical spacing of like 0.5 to 2 meters apart are those traces, which forms a grid pattern beneath our equipment. Now, the target impedance is we have to have less than 1 milliohm at radio frequencies. So, like the frequencies less than 10 megahertz or around 10 megahertz. This mesh, this SRG, basically equalize the potential difference between the equipment traces or preventing ground loops. So it also provides a low impedance return path for high frequency transient currents and stabilizes the voltage reference planes for high speed digital system. Another definition is common mode voltage, which is the voltage difference between the neutral and the ground at the input terminals of the electronic devices. It should be based on the recommendation of IEEE 1100, should be less than 1 volt RMS. And the reason that it's important is that the excessive CMV, common mode voltage, basically injects noise into the digital logic circuits and causes like intermediate logic toggling or like serial communication errors or resetting of the power supplies. The last definition that we want to mention is bounding network interface, which is a designated connection point where the signal reference system, that SRG that we talked about, interfaces with the building's grounding electrode systems. Okay, now it is important to prevent floating ground potentials, okay, and control circulating current by providing a single low impedance bounding point. Okay. The recommendation is to use in this standard is to use solid corrosion resistant bonding, okay, and low impedance connection to make sure the high frequency transients are basically diverted safely to the building ground. Now, there are some fundamental principles of powering and grounding based on IEEE 1100. Now, this standard views the system as 4 interrelated subsystems. Okay, it is power distribution, grounding subsystem, signal reference subsystem, and electromagnetic compatibility. Now, when we talk about the power distribution subsystem, excuse me, the definition and the function is that this subsystem is responsible for delivering the electrical energy to the equipment within the acceptable voltage, current, and frequency tolerance. Okay, so the requirement mentioned in IEEE 1100 is, like, for example, voltage stability, which we have to like maintain the nominal voltage under the full load condition within the plus minus 5%. Or we have waveform integrity, which means total harmonic distortion, that THD that we have should be less than 5%. We should have transient mitigation, which we have to suppress the voltage sags or swells, and high-speed transient, which we normally do that using isolation transformers or UPS system or line conditioners. Now, we also have to have load segregation, which separates sensitive loads from inductive or nonlinear loads, so we could prevent noise propagation. Okay, So if we have a poor power distribution, it can lead to equipment lockups or under voltage lockouts or overheating due to harmonics. Now, next subsystem that we mentioned is grounding subsystem. This subsystem provides the reference point for both safety and operational voltage. Now, in IEEE 1100, the grounding is not just as a safety feature. It also has a functional infrastructure element for the sensitive electronic devices. Now, the requirements mentioned in the IEEE 1100 is, for example, the ground impedance. Okay, is one of the requirements, which should be less than a 1 ohm from the equipment to the signal reference grid, and less than a 1 milliohm at the radio frequency in high-speed digital systems. Now, we have to also, there's recommendation about the topology selection, which we have like single point grounding that is used for low frequency analog or audio system to avoid circulating current. We also have multi-point grounding or hybrid, we call it also hybrid, which is for high-speed digital systems, so we could reduce the impedance to the high-frequency transit. We also have a requirement for bonding network interface, which is a single connection point between the SRG and the building grounding electrical system. So there is a requirement for that aspects of the grounding subsystems in the IEEE 1100. Now, next subsystem is the signal reference. Now, this basically establishes a uniform equipotential reference plane that is used for all the interconnected electronic equipment and makes sure the signal integrity and the noise immunity. Now we have several requirements for that. One is the signal reference grid, which is as we mentioned is a copper mesh bounded to all the equipment racks, cables, trays, and shields that make sure that signal reference stability. We have a requirement for common mode voltage control, which is the voltage between the neutral and the ground, and it should be, as we mentioned before, less than 1 volt RMS at the equipment input. Okay. Now we have another requirement for this subsystem, which is bonding and shielding, which all the equipment chases and cable should be bounded to the SRG so they could eliminate the potential differences. Now, we also, as we mentioned, the last subsystem is the electromagnetic compatibility. We also have that subsystem. You may have heard about the EMC systems, which basically controls the propagation of the radiated and conducted electromagnetic interferences. So we can maintain the equipment compatibility and regulatory compliances. There are several also requirements in IEEE 1100 for this specific subsystem, which one is having EMI or RFI filtering and shielding. For another one is the grounding for EMC, which basically that SRG that we mentioned provides a low impedance return path for high frequency currents, which proper bounding of the cable shields at both ends reduce radiated emissions. We also have isolation requirements, which basically physical and electrical separation of the noisy equipment from the different zones of those sensitive electronic equipment. Now, this standard also covers some performance criteria for the critical power environment. The first parameter is the grounding impedance. As we mentioned, our limit should be less than 1 ohm for a connection between the equipment to the SRG. We have a performance criteria as common mode voltage. Again, we mentioned it should be less than 1 volt RMS. We have a zero crossing distortion that it should be less than 1%. Let's talk about it. This zero crossing distortion is the distortion of the AC waveform when the AC waveform crosses the zero value, 0 point in our in the time varying behavior that it has. This basically very critical for the timing in a logic circuit, like those circuit in switch mode power supplies that relies on an accurate zero crossing detection. And if we don't meet these kind of like criteria, it would end up in a misfiring of the power electronic devices, leading to some lockup or erratic voltage regulation or increased harmonic generation because of the improper firing angles. Now, we also have a performance criteria for voltage sag depth and duration, which the depth of the voltage sag should be less than 10% of the nominal voltage. We shouldn't have less than more than 10% of the nominal voltage in voltage sag, and the duration of that voltage sag should not get to the 10 millisecond and higher. Now, we also have harmonic voltage distortion criteria, which has been mentioned. It is based on IEEE 519, and it should be less than 5% THD. This is voltage distortion. IEEE 519 has limitation for current distortion and voltage distortion. And please make sure that you distinguish this 5% is for THD. On that IEEE 519, we have two parameters that quantify the distortion. One is THD, which is total harmonic distortion. Another one is TDD, which is the total demand distortion. This 5% is for THD on a voltage. Okay, so this is important to make sure that we consider all those specific definition. Now, we have concept of the ground as a signal reference. Let's talk about it. Now, traditional grounding basically treats the equipment grounding conductor primarily as a pass to clear the fault current. Okay, so it is designed to carry the fault current temporarily during the fault event. Okay, the impedance values on those systems are chosen for fault current magnitude, not for signal stability. And there is no consideration of a high frequency transient for logic circuit integrity. Now, there is a limitation on that for sensitive electronic equipment, which basically traditional safety grounds can be electrically noisy. Why? Because we have circulating ground current induced by other nodes, or we have an impedance that is too high when we talk about the high frequency transient. Okay, so this result to logic errors or random resets or serial communication faults, data corruption. So IEEE 1100 takes another approach. It basically reframes the ground pass as an operational reference plane. Okay, so based on the IEEE 1100, that ground pass should be electrically quiet, so it has the minimal transient noise. It should have a low impedance across both power frequency and high frequency. Okay, and it should be free from circulating current. Okay, so that circulating current can cause voltage offsets in the system. Now, why it is important, one functionality is one aspect is the functional performance, another one is the signal integrity. We should have noise immunity, which is suppressing the high frequency transient. And we also should have the EMC consideration and automatic compatibility consideration to prevent the ground from acting as an antenna or electromagnetic interference source. Now, there are some design principles. We already mentioned some of them. The low impedance grounding, we have criteria for the circulating current control. We have like a different topology, like single point grounding or multiple point grounding that makes sure that we control the circulating current under the limit that we have. The bounding network interference that we talked about before make sure that we have a control signal bounding point. So it is between the signal reference system and the building's grounding electrode systems that we could prevent to have a floating grounds, and prevent multiple neutral to ground bounds that causes loops. Now, if we do not have a good signal reference grounding, there are some consequences. One would be a manifestation in the sensitive electronic equipment, okay? Or for example, we could have unexpected logic toggling and analog noise in our system. Now, we have different, as we mentioned, different grounding strategy, okay? But why we have that? This is because we want to like providing a stable, low noise reference plane, okay, for those SEE equipment, those sensitive electronic equipment. So, and we are going to do that while meeting the safety and EMC requirements. Okay, now this distinction has a reason, and it's because different types of the system have different grounding needs. So these IEEE 1100 basically specify single point and multi-point grounding, and it do that depending on the operating frequency and the equipment sensitivity. Now, when we talk about the single point grounding, it means that all the ground terminates at a single common point. So it's like a short. There is only one bonding point between the equipment chassis and the building ground systems. So normally we use that in a low frequency, high sensitivity analog device like radio recording studio or medical imaging or low frequency RF systems. These single points sometimes is preferred in a low frequency system because the circulating current control is good in those systems because it eliminates the ground loops. It provides a clean reference, which is a single defined reference potential. So we have minimizing analog measurement errors, but there is a limitation. When we have a high frequency, these single point grounding would face a high impedance for those frequency. That means like a long ground basically leads to as basically act as an inductors at radio frequency and high speed digital frequencies. So basically, when we have high frequency, it would increase the impedance. As you know, the inductor's impedance is J omega L. When we have high frequency, it means we have high impedance, and it creates problem for the sensitive equipment that works with the high frequency. Another strategy that we mentioned for grounding is multi-point grounding, which is basically made at that grounding, the multiple ground connections are made at various points. It could be like a mesh or star configuration. And it's normally implemented as the signal reference grid that we talked about at SRG. The application of this type of grounding is normally a high-speed digital and a broadband system like data centers or broadcast or high-frequency industrial automation system. But why this multiple grounding sometimes is preferred is because it has a low high-frequency impedance. Okay, so multiple short parallel ground paths reduce inductive impedance, which provide a fast transient dissipation. It reduces the radiated emissions and susceptibility to external EMI by providing that low impedance return path. But this multi-point grounding also has its own limitation. One would be the circulating current possibility. So when we have a low frequency, that MPG, that multi-point grounding, can create ground loops, which introduces the noise into the analog systems. Now, we mentioned we have some hybrid grounding, which is the mix of the single point and multi-point. It is for balancing the advantage and disadvantage of the both. So that is application of that hybrid is mostly in the modern facilities like data centers or aerospace or hospitals, because systems often contain both analog control system and high-speed digital electronics. Now, let's now that we talked about how we could connect the grounding system, the all grounding system to the building grounding, let's talk about the power distribution design defined in this IEEE 1100. Now, the objective of this design is to provide a clean, a stable, and uninterrupted power for the sensitive electronic equipment. And it does that by minimizing the voltage fluctuations and waveform distortions and the noise propagation. Now, there are four key design objectives based on the IEEE 1100. One would be the voltage stability. We mentioned there is criteria to maintain the nominal voltage within the plus minus 5%. And it is under full load condition. Please note that. We have waveform integrity as a criteria for power distribution, which is basically means the total harmonic distortion and zero crossing distortion should be limited based on the criteria of the defined in the IEEE 1100 and IEEE 519. We have the ground reference quality as another aspect of the power distribution, another kind of like point that we need to keep in mind when we're designing the power distribution system. This is the recommended design criteria is, for example, maintaining a low impedance bonding and keep the common mode voltage under the defined threshold. We have another aspect that we need to have in our power distribution is load isolation. So basically, the loads in our system should be physically and electrically separated. There are some definition for the zones in our system. So we could have like inductive loads or nonlinear loads. All these defined, and we have to segregate them. So the loads should be isolated from each other. Now, to do that, we could have several topology in our power system. Okay, so this is basically this power distribution topology determines the reliability and the fault tolerance and the availability of the power. And as we mentioned, the IEEE classifies those power distribution mainly into three main topologies. Okay, radial distribution, primary selective distribution, or secondary selective distribution. Now let's talk about those in detail. Now, the radial distribution is a single feeder that supplies the power from one transformer to multiple panels, like in a tree-like structure. Okay, so is the simplest and the lowest kind of like cost topology. It is a single point failure vulnerability. So any fault in upstream affects all the downstream load. Normally, we use that type of topology in non-critical facilities or low priority zones, like office spaces or lighting system or low priority manufacturing areas. As we said, there are some advantages. One would be the cost effectiveness of this topology and easy to for maintenance. It has a simpler design and needs fewer components, but for the critical sensitive equipment is not recommended because there is no redundancy, and a voltage size or transient from one load propagate to all downstream equipment. Now, next choice for the topology of the power stream is the primary selective distribution, or as we call it, looped distribution. So in this topology, we have two independent feeders, each from a separate transformer or power source, which is arranged in a loop configuration. Okay, a manual or automatic transfer switches basically enable alternating power routing during a fault. So basically, one source can fail while the other maintains the service. That switching between them can be manual or automatic based on the criticality of the system. It is normally used in a medium-sized critical system like hospitals or university laboratories or manufacturing with moderate downtime tolerance. The advantage of this topology is that it improves the reliability compared to the radial distribution, and we have a fault isolation possible with minimal downtime. There are some disadvantages into that for that topology. One is that it doesn't have a instantaneous power transfer unless it is fully automated. It is more expensive compared to the radial distribution because it needs extra feeders and transfer mechanism. So we need to choose. Is a trade-off basically. If you want to like choose between the radial distribution and primary selective distribution. Third topology is the secondary selective distribution. Now it's a fully redundant dual power source, okay, that mostly operating in a parallel or hot standby. Now it's the highest reliability, like tier 3+ or even tier 4 data center compliances. It is automatic. It instantaneously transfers during a failure of a one source, okay, and normally is used in a mission critical sensitive electronic equipment environments like data centers or surgical suites or telecom hubs. Okay, the advantages of this topology is that we have full redundancy that makes sure continuous uptime. It supports load sharing and hot maintenance, but on the other hand, there is a high installation and maintenance cost for this topology, and it requires a careful design so we could avoid circulating current between the sources. So we need to like see consider these trade-off, but we want to like choose the power system topology between these three choices that IEEE 1100 gave us. Now, in the sensitive environment, the transformers are not just the step up or step down devices. They also work as filters to attenuate the harmonic currents and common mode noises. They could used as an isolation barriers, so it would providing a galvanic separation between the utility sources and the sensitive loads. And it could be a noise sinks, shielding the equipment from the transient and high frequency disturbances. Now, these sensitive electronic devices that we talked about are highly susceptible to those harmonic distortion, voltage transient, and common mode noises. Okay, so this is makes the transformers kind of like a very critical role when we talk about the mitigating of those disturbances. Now, we have several criteria for selecting of the transformer based on the IEEE 1100. One is the K rating. Now, it is for harmonic rich loads. The definition of the K rating is that K rating indicates a transformer's ability to handle the harmonic currents without overheat. So we know that the harmonic currents primarily caused by nonlinear loads, and they increase the eddy currents and basically the losses in transformer winding and core, meaning you have an overheating problem. Now, for in IEEE 1100, the recommendation is that we have to have this minimum K13 rating for the environment with a significant sensitive electronic equipment loads. Okay, I mentioned those rating and values of nonlinear load currents in the table that you see in the slide. The higher K rating, like 20 or 30, could be recommended for extreme harmonic conditions. And is important because a non-K rated transformer will overheat and fail permanently when we have a harmonic rich condition. Now, another criteria for choosing the transformers in our power system is the impedance rating. So the recommendations from the IEEE 1100 is that we have to have the impedance range of 2 to 4%, okay, in a standard power frequency impedance. Now, what is the rationale? The low impedance is less than 2%. It allows a high inrush currents, which makes breaker tripping or voltage dips for other loads. If we have higher impedance, more than 4%, it means excessive voltage drop under the dynamic load change. Okay, so this standard requires an impedance between 2 to 4%. Now, another aspect of the transformer that we need to keep in mind when we want to choose the proper transformer is the ground resistance. The limits recommended by IEEE 1100 is that we should have less than a 5 ohm for the service entrance ground electrode system. Okay, this is the last 5 ohm is target for entrance ground. Okay, but IEEE 1100 emphasizes that we have to have less than 1 ohm for the signal reference. Make sure that you distinguish these two. So the purpose of this less than 5 ohm is to make sure that we have uniform ground reference for sensitive electronic devices, and it prevent the potential difference that basically could cause a common mode notices. Now, in our power system, in this topology, another component that we need to pay attention when we want to like design or choose between the option that we have is a panel board. Okay. Uh, the purpose of choosing proper panel board and basically a branch circuit design, when we talk about the sensitive electronic equipment, is to make sure we have a clean, and stable, and noise-free power delivery for those sensitive electronic devices. So we could minimize the harmonic interactions, we could control the common mode noises, and we could prevent the transient propagation between the loads. If we have a poor panel load or branch circuit layout, uh, this could be one of the end up as one of the most common causes of the logic malfunction or communication errors and the intermittent resets in those sensitive devices. The recommendation for that has a several aspects when we talk about the recommendation of the IEEE 1100. One is the isolated ground bars, which is the dedicated ground bars that connected directly to the signal reference grid, is independent of other equipment grounding conductors. Why we have this recommendation? We need that to stabilize the ground reference for sensitive equipment by avoiding the noise coupling from the building structure ground and providing a low impedance, we said less than 1 ohm, for high frequency transient. No, so each panel basically serving those sensitive equipment should have an isolated ground bar bounded directly to the SRG. Okay, is should not connected to the conduit or building still directly to the SRG is the path for those bars. Now we have to also make sure that we maintain the neutral to ground bond only at the source transformer. Okay, why? Because we have to prevent the parallel neutral ground passes. These could cause circulating ground currents or introduce common mode noises. And basically, if we don't do that, that bonding the neutral to the ground at sub panels, it could create multiple current return paths, which induce the ground loop voltages. Now, another requirement for those panel board is to avoid shared neutral. Okay, we have to provide separate neutral conductor for each branch circuit. So if you have a nonlinear load that generates like triplet harmonics, like third harmonic, ninth harmonic, or 15th harmonic, that do not cancel in the neutral, but actually is add up arithmetically. If we have a shared neutral, it could lead to overheated neutral conductor. So we have fire risk here. Or we could have a voltage distortion and noise coupling between those circuits. Now, in the panel board, we also have to have load segregation. So we have to separate the panel board by the load type. We have zone A, which is the sensitive equipment only, like computers, PLCs, for medical imaging. We have zone B, which is the mixed use loads with isolation, transformers, or filtering. And we have zone C, which is the high interference loads like motors or welders or HVAC. Okay, so this is important. We have to make sure we consider all those aspects when we want to like design and implement the panel board in our system based on IEEE 1100. Now, we mentioned load segregation and filtering several times. This is because we wanted to isolate sensitive electronic equipment from the electrical noise, transient, and harmonic that are generated by other type of signal. Okay, so that electrical disturbances can propagate through shared feeders and can cause data corruptions or logic errors or resets in those sensitive equipment. And if we have a proper, excuse me, load segregation, it prevents that cross-coupling of those disturbances by using dedicated feeders and physical separation. Okay, the strategy that is defined in IEEE 1100 for segregation is defining three distinct zones based on the sensitivity to the power quality and the level of interference generated by the equipment. We mentioned briefly those three zones. We have zone A, which is a sensitive electronic equipment only. It is dedicated power distribution exclusively for those sensitive equipment, electronic equipment, like servers or medical imaging or broadcast. We do not have shared circuit with inductive or nonlinear loads in this kind of system. The isolated ground bars bonded directly to the signal reference grid. Okay, we have a K-rated transformer, K13 and higher, and we have a properly coordinated surge protection. Okay, the wiring on those zones should be twisted pair or shielded conductors, so we minimize the EMI in our system. Zone B, the second zone, is mixed use loads. Okay, those panel boards supplying a mix of sensitive equipment and general equipment, considered as these kind of like zone B, but they have some mitigation measures too. Okay, so there is an isolation transformer that is required for these zones, so electrically separate the sensitive equipment from the noisy loads. We should have EMI filters that are installed on nonlinear or inductive loads within the same panel. And we should have a physical separation of the circuits. Okay, so all the sensitive equipment are routed separately from the high interference circuit. We have zone C, which is the high interference loads. So there are loads that generate significant electrical noise or transient or harmonic distortion. It could be like motors or welders or elevators or compressors, those kind of like loads are considered as zone C. There are some design requirements. One would be they have to be completely separated. They have to have completely separated feeders and panel boards. So they should not share any feeders, transformers, or neutrals with the zone A. Okay. They have to have active or passive filters, okay, at the sources that contain noise for harmonic mitigation, basically. And they have to have physical separation, meaning the cables routed away from the zone A circuits should be separated so we could reduce the inductive or capacitive coupling between the cables that feed the zone A and zone C. Now, we want to create a high quality and reliable power system. So one aspect is to use UPS, uninterrupted power system. The purpose of UPS and those bypass infrastructure is to make sure we have a continuous, clean, and stable power. Okay. And we have to make sure that we have those qualities in power during the utility disturbances or sag or outage of the disturbance of the power sources. Now, the recommended UPS type for these sensitive devices is online double conversion UPS. So it works as AC to DC to AC conversion. So the incoming is AC, then it's rectified to DC, filtered, and then reverted back to the AC. Now, the voltage regulation for these for the specification of these equipment under IEEE 1100 is that it should have less than a plus minus 2% voltage deviation under the dynamic load change. The frequency should be, deviation should be less than 0.1 hertz plus minus 0.1 hertz. And the transfer time is another recommended specification for this equipment, which the zero, we have to have zero transfer time during the outages. Okay, now we have other type of UPS which are not recommended for high critical sensitive devices like line interactive UPSs. The reason that they are not ideal is that they have a limited sag surge control and they have a slower transfer time. Okay, we have also standby UPSs, but because they have like a brief power interruption during the transfer, they are not acceptable for sensitive electronic devices. Now, we also have bypass infrastructure, which allows continuous power to critical loads during the UPS maintenance or UPS failures or overload of the UPS systems. We have a static bypass, which is an automatic pass transfer. When we say pass transfer, we mean fast transfer, we mean less than 4 milliseconds. And this is for when the UPS fails or overloaded. It makes sure an uninterrupted power by transferring the load directly to the utility or the generator. Okay, those static bypass should be properly coordinated so we could avoid the circulating current and voltage transient when we have the transfer, when we are transferring between the sources. Now, we also have maintenance bypass, which are manual bypass, okay? And they normally use during the UPS services. We also have a transfer switching method, which is break before make. This is recommended by IEEE 1100, and it prevents parallel source connection. So it's avoiding circulating currents. This is important because we have make before break transfer switching method. That make before break is not recommended in for the sensitive electronic devices, as basically temporary source overlap can introduce the transients or overloads, and this is the reason that these make before breaks transfer switching methods are not recommended for sensitive devices. Now, when we want to provide a stable low noise signal reference and at the same time maintaining the fault clearing safety, we need to have a proper grounding architecture. Now, it is important because sensitive electronic equipment is highly susceptible to the common mode noise, ground loops, and high frequency transient. The chosen architecture directly affects those aspects like the signal integrity or EMC and equipment reliability. Now we have three types of architecture. One, as we mentioned, is a single point grounding. when all the equipments and the signal grounds terminate at a single common bonding point. We have a multi-point grounding. We already covered that. It is when equipment is grounded at multiple points, normally arranged as a mesh or a star patterns. And we have hybrid grounding, which combines the single point and multiple grounding. We already talked about that. I don't want to have an over explanation about those concepts in favor of saving some time. Now, we mentioned several times that one of the key components that in the grounding system is the signal reference grid, the SRG. Now, that SRG is a mesh of interconnected conductors that forms an equipotential reference plane for the electronic equipment. Now, it is important because it provides a stable, low impedance signal reference, and it shows uniform voltage potential, so we don't have ground loops and common mode noise, and is essential basically for higher speed digital systems. Okay, now there are several recommendations when we talk about the IEEE 1100 about the SRG. One would be the construction, like material. It should be copper strips. The spacing between those strips should be between 0.5 meters to 2 meters. Okay, and the layout should be beneath or integrated into the equipment room floor. Okay, so the mesh must cover the entire area. Okay, now we have an impedance target. Okay, so we have to have less than 1 milliohm at RF frequencies. And the bonding network, the equipment bonding, also have some requirements. One is that every equipment rack or cable tray or shield and ground conductor should be directly bonded to the SRG. It should use short wide bonding straps so we could reduce the inductions. Okay, and the purpose is to prevent differential ground potential between the equipment, which can basically cause common mode noises on the signal lines. Now, we also have to have a bonding network interference, and the SRG must connect it to the building ground electrode at a single designated point. Okay, now these SRG, okay, improve the signal integrity in our system. It enhances the EMC situation in our system. It gives us a noise immunity, and it increases the system reliability when we talk about the sensitive situations. Now, we also mentioned that these systems should also have surge protective devices, which are voltage clamping or diverting devices that are designed to protect the sensitive devices from transient overvoltages. Those overvoltages can be caused by lightning strikes or switching surges or inductive kickbacks. It is important because even a microsecond level transient can cause a logic error or data corruption or permanent damage in the component. Now we have several classifications for the surge protected devices. One would be the type 1, the service entrance, which is installed between the utility service and the line sides of the main service disconnect. The function is that this high energy surge it would diverse the high energy surge from the external source, so it would not propagate downstream into our system. We have distribution panel devices, type 2 SPD. They are normally placed on the load side of the main service disconnect. So it is at the distribution panels or sub-panels. And the function is to intermediate clamping for residual surge that pass through the type 1 or generated internally by the equipment switching. Now, type 3 is point of use protection, which is basically installed close to the sensitive equipment. Is normally like a plug-in strips or integrated equipment level modules, and it gives us the final stage clamping to make sure that only low lead through voltages reach the sensitive equipment. Now, we have some requirements for coordination between the SPDs. So this IEEE 100 strongly emphasizes the coordinated SPD installation, so we could make sure proper energy dissipation across the levels. So there is a hierarchy of the clamping voltage. Okay, so the type 1 is the highest voltage, the type 2 is the medium voltage, and type 3 is the lowest voltage. We have to have a physical separation at least 9 meters, 30 feet of a conductor length between those stages. We have to have a proper grounding, so we make sure that we have a low impedance bounding. That criteria was less than 1 ohm to the SRG. Okay, and we have to have a dedicated circuiting, so SPDs should be installed on dedicated breakers so they could prevent false stripping of the circuits when we talk about the sensitive electronic devices. Now, so far we talked about the IEEE, we covered the key aspect of this standard, but you should note that the IEEE 1100 isn't just a guide, okay? It is a blueprint for electrical reliability in the modern or mission critical facilities. So it moves the conversation from the code compliances to engineering performance. If you follow this standard, you are not just keeping the lights on, you are making sure that the data flows, processing runs, and lives are protected. This is our discussion for today. Thank you for your attention. If you have any question, let me know.